Okay, the next thing we're going to look at are some transformations. And so just to remind you of the transformations you know from grade 11 and earlier in this course as well. We know that we have A, K, D, and C that apply different transformations to a base function. And so in a logarithmic function, you're going to see all four of these transformations as well. The value of A looks at a vertical stretch or compression. So when A is greater than 1, it stretches the graph vertically. And when it's between 0 and 1, it compresses the graph vertically. If it's negative, you know that there's a reflection along the x-axis. The K value is a horizontal stretch or compression. We know that as well, so the graph will either get wider horizontally or more narrow. If it's negative, there's a reflection in the y-axis. The D value looks at a horizontal translation, so shifting the graph left or right. The C value looks at a vertical translation, so shifting the graph up and down. Just a quick note, remember that vertical transformations are values that you see that are outside the brackets, and horizontal transformations are values that you see that are inside the brackets. Remember also that the order of transformations is important. You want to make sure you stretch and reflect the graph first before you translate or shift the graph after. And because we are looking at logarithmic functions, and logarithmic functions have vertical asymptotes, what you'll notice is that anytime you shift the graph left or right, so any horizontal shift, will also affect the vertical asymptote. So think about if my pencil represented a vertical asymptote, the only way that the vertical asymptote would move is if the graph moved left or right. Okay? So that's something to think about. Okay, so transformations of logarithmic functions. You'll note again that the effects of each transformation are still exactly the same. So in other words, the way A, K, and D, and C affect the base graph is exactly the same as any other function that we've looked at. Okay, so here's any base function. That's why I have an f in the equation. And here's the same thing but with the logarithmic function. So you'll notice that K and D are your horizontal transformations. They happen to be inside brackets with the logarithm applied to it. And C and A are your vertical transformations, and those are the ones that will stretch or reflect or shift the graph vertically. Okay, so logarithmic functions. How do we graph logarithmic functions? So, to graph a logarithmic function of the form y equals a log k of x minus d plus c, the first thing we need to determine is what the base graph is. So depending on how the equation is written, we need to determine what the base graph here would be. Okay, remember from last year when we looked at exponential functions? When you had a graph like y equals 4 to the exponent x, or y equals 1/2 to the exponent x, these were examples of exponential functions, but both of these are base functions. Okay? If this was the base function, different transformations can be applied to it. So you can stretch the graph, you can reflect the graph, you can shift the graph. Same thing for y equals 1/2 to the exponent x. Okay, so what we need to do first is determine what the base graph is. From there, we need to determine what the key points of the base graph are. So it depends on what your base logarithmic function is, and you'll see some examples on how to determine what the key points for the base graph will be. Essentially, what you're looking for is what value of x you will have an exponent of 0 applied to, and what value of x will have an exponent of 1 applied to it. Okay, so let's say you had y equals log base 2 of x. So let's say this was our base function. So what I need to think about is if my y value is 0, what does the value of x have to be in order to have a y value of 0? So I know that this means 2 to the exponent 0 gives me some answer of x. So in other words, this is 2 to the exponent 0 equals some answer of x. And I know that that answer would be 1. So for example, in this case, my x value would be 1. Okay? If I was trying to figure out what value of x would make the y value or the exponent 1, what that would mean is I have 2 to the exponent 1 equals x. And so I know 2 to the exponent 1 is equal to 2. So here's my key points if I was looking at a logarithmic function with a base of 2. Now this is going to change because it really matters which base you're looking at for your logarithmic function. So it's not always going to be 1 and 2. It's always going to be dependent on what the base function is. Okay, but I will tell you, to make it work a little bit easier, that the x value here will always be 1. Remember when we talked about an x-intercept of 1 and 0? That's the reason why this one will actually always be 1 and 0. But this one will change, and it'll end up being the base, the actual value of the base function. So let's say you had a base of 5, this x-coordinate would be 5. If you had a base value of 10, this x-coordinate would have been 10. And then the way you apply your transformations is exactly the same as what you've always done. So that's not much different. The only other thing you need to remember is where the new asymptote is. Normally your asymptote for the logarithmic function is a vertical asymptote at x equal to 0. As soon as you shift the graph d units either to the left or to the right, the vertical asymptote will also change as well. So depending on what your horizontal shift is, you'll be able to determine what the vertical asymptote is. Okay, from there you want to create your mapping formulas and then find the transformed points, and then you're going to graph the new transformed function with one end of the function approaching the asymptote and the other end of the function extending towards either positive or negative infinity, depending on what the transformations are that are applied to the function.